Hello, it's Scott Manley here, back with episode 6 of my viewer questions series, answering questions posed by supporters over at my Patreon. And we're going to get right down to business with Potato McGrills, who asks, I would love to know more about the computer aspects of a satellite, how much memory, processor speed, cooling needs, etc. Well, let me tell you, if you want to know about computers that flew on the Apollo program, I actually have some good videos about that I can link. But currently, if you're going to fly a spacecraft to space, you will generally put a hardened CPU in it. Although nowadays there are actually plenty of people putting regular CPUs up there. But, you know, the subject of radiation hardening CPUs and other electronics is quite a large field. One of the things you'll find is that they'll use things like silicon on insulator and silicon on sapphire technologies. They will use larger feature sizes because they're typically many years behind, and also because large gate structures on the chip make them more secure against ionizing radiation, right? You know, the amount of radiation or the energy in each particle isn't generally changing over time, but if you're shrinking your features down, they're getting more and more vulnerable because the amount of energy that they're working with is getting smaller. So, for example, the compute unit at the core of the Perseverance rover is based on this DAC. What is it? It's basically based on a PowerPC processor, but it's a specially radiation hardened one. It's roughly the same to the processor that was in the very first iMac back in like 1997. Its feature size is about 200 nanometers. For comparison, my latest MacBook with the M1 has a 5 nanometer feature size, which means in the same space that you could fit one gate on this processor that's on Mars, you could fit like wait a second, 1600, right? Because it's 400 by 4. It's lots. It's massive density increase, but that makes it much more vulnerable to radiation coming down. You'll do things like change out the RAM designs. Modern computers, they will use RAM, which stores data in little tiny capacitors, little bundles of charge. But that's actually much more susceptible to radiation coming in and changing that, because they literally can bring in charge with them or knock them out of the substrate. So it's actually common to see spacecraft using SRAM instead. That's where they have a bunch of gates sort of interconnected to regulate each other and store things either as a 1 or a 0. Anyway, look, that's a whole massive thing. It is worth noting, on Mars, the Ingenuity helicopter is built from an off-the-shelf drone platform. Therefore, it's actually using an ARM processor, which is close to that which you would find in a phone. And they can sort of get away with that because Mars is a less dangerous environment in terms of radiation. It's still higher than the Earth, but it's not like deep space. Okay, question. Stephen O'Leary asks, on a Mars mission, what are possible fuels? If liquid oxygen is used, how will it be kept cold and liquid? Well, okay, on Earth, we keep liquid oxygen cold and liquid by having insulation to stop the air getting in and condensing on. On Mars, that's actually slightly easier because there's a lot less atmosphere getting in. But, you know, as you go further away from the sun in general, the temperature drops, and you can actually build a passively cooled system that is good pretty close to the sun if you are in deep space, because sure, one side is fully exposed to the massive heat of the sun, but the other side is exposed to deep space where the average temperature is 2.7 Kelvin. So you just need to make sure that you emit most of your heat off towards deep space and try and minimize the amount you absorb from the sun. And you can sort of get away with that on Mars. It might be that you need to have some sort of active regenerative cooling system, that anything that vaporizes gets cooled back down. But I don't think it's that hard. Mars is a lot easier than you would imagine on this front. So yeah, for Mars, the full of choices are liquid oxygen and methane, because you can make methane from the carbon dioxide, and if you can find some water, you can get hydrogen to make methane. If you can't find water, by the way, you can either bring your own hydrogen, such as Robert Zubrin suggested, or you could try building something called a carbon monoxide oxygen rocket, and that's where you just take the carbon dioxide in the atmosphere, take off an oxygen, and you can actually burn those later. The problem is the ignition in test systems has been pretty rough. That is a problem that would probably be solved if it was necessary. Okay, we have two people that both asked at the same time about Lagrange points. Andrea Sperini asked, I've always been fascinated by Lagrange orbits, and what is the launch profile for such destinations? And that turned into a bit of a joke. Stephen H., again, Lagrange points and related gravity phenomena. What are they all about? So, most orbits that we talk about, we're treating the sun or the Earth as the center of mass, and we just approximate a single orbit around that with no other effects. But if you have two objects orbiting each other that are massive, then you can't do that once you get sort of to halfway distances. There are points basically between the Earth and the Moon where the orbit isn't sufficiently stable for long-term use. Like geostationary is probably okay, but the problem with geostationary orbit is it gets bent upwards due to the effect of the sun and the moon. So anyway, Lagrange points are 3 points where the rotation of the system, the gravity of the objects all cancel out, and the object can sit there more or less without any thrust or whatever being applied. These are called Lagrange points, and they're called L1, 2, 3, 4, and 5. L1 is the point between the two objects where the gravity balances out. L2 and L3 are on either side of the two objects. So like if you look at the Earth, L1 is the point between the Earth and the Sun where gravity balances out. L2 is the point on the far side of the Earth where the gravity all balances out. And L3 is the point on the far side of the Sun, almost identical, where you can put an object and it is too also sort of balanced there. And then there's two other points called L4 and L5, and these are points that form an equilateral triangle with the two massive bodies. And the one we use all the time are L1 and L2. We put scientific spacecraft in L1 and to study the sun, right? So if you want to study the sun, you put it between the sun and the Earth so it never gets eclipsed. And we have things like SOHO, Discover, and all the other solar observation spacecraft. And by the same token, if you put space telescopes out at L2 on the far side of the Earth, things like James Webb Space Telescope is going to be there. They have unblocked view of the sky continuously, and they're kept close to the Earth so they can be controlled. So that's what those are all about, but I should probably spend some time about looking at that. AMK. Hi Scott, I just came across the story of 2020 SO asteroid that turned out to be a Centaur rocket from the 60s. Now that we're sending stuff to Mars again, maybe it's a good opportunity to talk about what happens to the stuff we send out of Earth orbit. Will any of it come back to Earth? And the answer is yes. Lots of things that will be sent out into deep space have the potential to eventually come back, but space is really big, so generally they don't come back very often. Anything you're sending out to Mars is highly unlikely to come close to the Earth. And in fact, it's interesting, if you're sending like a Perseverance to Mars, the Centaur upper stage that boosted it out that way, after it was dropped off, it actually performs another maneuver to make sure it avoided Mars, because they don't want any of these stages approaching Mars. But equally, it's not coming back to Earth anytime soon. So things like 2020 SO, that I believe is one of the Surveyor spacecraft, which was a lander that landed on the moon. Now, that meant that it wasn't going that much faster. In fact, I believe, it wasn't. Originally, it was in a Earth-Moon orbit, a highly eccentric one. And the moon, its gravity, kicked this thing off out into space, but it wasn't moving very fast. So it had spent a lot more time near the Earth and periodically can come back. Another example is J000203, which was the third stage, see this one up here, of Apollo 12, that also swung by the moon off into deep space and came back, and they found this asteroid and they were worried it would hit the Earth, and they looked at the spectra and said, that looks a lot like titanium dioxide paint, which is the white paint, or maybe it's titanium oxide. It's actually, there's quite a few bits and pieces in Earth, or the vicinity of the Earth, that are starting to turn up in asteroid surveys. And none of them pose any threats. There's nothing big enough out there to worry about. But hey, there was a fun story on Twitter that, like, Zach Wienersmith, who, he does the Saturday morning breakfast. I forget what it is. He proposed like a fun movie plot where the entire world's gut bacteria gets wiped out and humanity is suffering major digestive issues. And we have to go out into space and find poop from the astronauts that went to the moon. And I took that to the next level and said, how about Neil Armstrong brought back a moon plague that eventually, 50 years later, it all kills in. There's a catastrophic collapse of our gut microbes. And the only place is the people that never went to the moon. Apollo 10, they left their command module, Snoopy, and it ended up going out into deep space. Out there, there's some deep frozen astronaut poop, which has never been exposed to the moon vaccine or whatever, moon disease. So yes, Snoopy is the one that I would like to find, not for the poop, just because it's a cool thing. It's the only flown lunar module that hasn't been destroyed. Oh, wow. Sorry, major diversion there, but that's what you're watching this for, right? Robert B. How about a video on our launch ascent profiles? What would the different craft use? Why would different craft use a different one? How do they work in different planets and atmosphere? Well, this is all kind of a boring subject, to be honest. But no, right. So launch profiles, they're all about maximizing your efficiency getting from surface of the planet to your target orbit. And there are a lot of things to take account of. If depending upon how much thrust you have on each stage, if you have a low thrust second stage, such as the Centaur on the Atlas here, then you might have to take off in a steep trajectory so that the Atlas is moving upwards fast enough so that in the time that it takes to accelerate to its target orbit, it has enough time to do that. Falcon 9, on the other hand, it can fly a much more depressed trajectory closer to the Earth because its second stage accelerates much faster. And this difference, actually, the low thrust on the Centaur, was one of the reasons why NASA in 2005 basically said, oh, we're going to build Constellation instead of just putting crew capsules on top of these rockets that are already flying. And this was largely a political play because the politicians wanted to have an excuse to fund the existing shuttle suppliers. But, there's a paper called Black Zones or whatever. It's basically, there was a study that claimed that the black zones, the points at which the abort could happen on the Atlas, there were too many places where it would threaten the crew because they would be high up from this lofted trajectory, and if they didn't light the engine or if the engine only worked part of the way, they would fall very steeply down through the atmosphere and experience very high G-forces. As it turned out, that was a bunch of politics mainly, and it was very capable. The Atlas was more than capable of doing this, but all the same, when Starliner launches on an Atlas V, it has a dual-engine Centaur so that they have extra thrust and also they have a backup engine if necessary. So they can handle all this. There's other things, like if you go too low as well, then you will find that you're actually, you're getting much more aerodynamic resistance, and max Q happens at a higher altitude and you're going faster. And so you'll find spacecraft where they have a lot of thrust early on. They will sometimes fire the engine and then just do nothing until they fire the second engine because they're too low in the atmosphere after burnout of the first stage. And an example of that actually is the very first satellite launched by the US, Explorer 1, which launched on a Redstone rocket, which booted it up to this sort of arc trajectory. And then 30 seconds before they hit apogee, they started firing their last three stages to put them into orbit. Yeah, I think it's hard to really generalize about all these things, but sure, lots of things to talk about there. Yaroslav Gurikin. Love this new format, Scott. Do you have a favourite non-traditional fuel oxidizer pair? Kerosene LOX is great and LH2 LOX is awesome, but they are boring. I'm going to say one of the ones I find interesting is Syntin LOX. So Syntin was a synthetic petroleum. It was a replacement for kerosene that Russia came up with, or the Soviet Union, And this actually gave them slightly more performance than standard RP1. It basically was a way to buy more performance for their R7, their Soyuz, right? That's it sitting next to my Saturn V. It's 3D printed. And I think they're actually pretty much to scale. I think that's kind of cool because it just shows you that chemistry can do neat stuff. There are like, I've seen some interesting things that chemists have done where they've built stressed structures where, for example, they folded the carbon atoms into a cubic shape. And because these are sort of springs, when they break, they actually release more energy than you would normally get from these chemicals. But yeah, what else? Well, if you want to hear something ridiculous, there's a FUF and diethyl mercury, or dimethyl mercury. They're basically the really toxic one. FUF is fluorine, oxygen, oxygen, fluorine. It just gives you hugely more powerful oxidizer by making both the oxygen and the fluorine want to leave. And diethyl mercury, or whatever, yeah, incredibly toxic to the point of drops of that stuff getting on your skin will kill you, right? Slowly, over many years. And that came up. It came up because I was reading a story. It was a short story by Charlie Stross, right? He wrote Singularity Sky and the Laundry Files. And it was basically sort of like, the story was that the US had decided that these fuels were so dangerous that they should pretend that there was a program to use these for missiles and there was a special additive, and then leak this to the adversaries in the hopes that they would kill their scientists by working with this hideously toxic material and this oxidizer that would just explode. Look it up somewhere. Just look up for FUF and Charles Stross. Anyway, Omar Merling. I think this is probably the last one for today, or maybe not. Beyond Mars, and with colonizing Earth and our moon in mind, which would be the next best planet or moon in our system to place a human presence on, and how? Do we have any technologies that would make gas giants candidates too? I'm going to say that I don't think gas giants will ever be candidates for habitation. Jupiter, for example, the gravity is much higher. And you might think, well, it's just gas. Let's put big balloons in there. You know what? Jupiter is hydrogen. So you can't really have a lighter than hydrogen gas. You have to heat it. And that's basically a giant hot air balloon that's relying on, energy coming in. I don't see that being viable. I see that you might be able to put a space probe in there and have it fly around for a bit. But also Jupiter's atmosphere is big. And if you're moving at the speed of an airship, you're not going to see very much. You're not going to go very fast. All the same, would be cool to do. Saturn's kind of in the same boat, but its density is even lower, although its atmosphere there's less gravity. Anyway, the place I would go if I was going to build a colony, and sure, or say colony, if I was going to send people to live in a place long term and do science, Titan. Titan is great. It has a thick atmosphere. You don't need a proper pressure suit. You just need to keep warm and give yourself a face mask. It has all the materials you need to perform ISRU. It has hydrocarbons and it has ice, so you can extract water. You can create rocket fuel from the surface. The big thing it doesn't have is huge amounts of solar energy, so you can get a little, but like the clouds of Titan block what little solar radiation there is, and because it's like 9 AU from the sun, you're getting 100 times less solar power at that distance before you even account for the clouds. So it'd be a nuclear powered station of some sort, but I'm sure there's a lot to find out on Titan, and I would love to explore there. Also, the thing I like about Titan is the atmosphere is so thin that you could probably fly pretty much using human power with great ease. So you could skip around that surface with big wings flapping or whatever for exploring. You could have like flying packs. Wouldn't that be great? Oh, man. Yeah, Titan, I think, is a really good option. There are other ones that you might want to, check out. I mean, the atmosphere is really important because it protects you against radiation. So you can look at things like Enceladus and say, well, that's really interesting because there's oceans there, but it's higher radiation environment on the surface because there's no atmosphere. So yes, I think that's enough for today. We're getting towards the end of the first post. Would love to. We're going to have to start getting to the later posts, but thanks for everyone for asking questions. I'm Scott Manley. Fly safe.